All right, hey guys, I'm back. So if we can, if you could turn to page 2 of your sequences packet, we're going to talk about an arithmetic sequence versus a geometric sequence. All right, so an arithmetic sequence is just a sequence of numbers where you add to get from one term to the next. So for example, let me just make one up here. Let's say we had, let's do this. We'll do 5, 8, 11, 14, and so on. Okay, what you can see is our first term here is 5, and in order to get from one term to the next, we're just adding on 3, right? 5 plus 3 is 8, 8 plus 3 is 11, 11 plus 3 is 14, and so on. So we're just continuing this on. Now there's two different ways that we can write a formula for this. Recursive we had talked about in the last video. So if we wanted to make a recursive formula for this, we could just say the first term, right, a sub 1 is equal to 5, and a sub n would be equal to the previous term plus 3. So the previous term would just be 1 less than this term. So if this is a sub n, we want to do 1 less than this. It would be a sub n minus 1. So it would be a sub n minus 1. And then we said that we are adding 3 to that term, plus 3, because that's how we're getting from one term to the next. Now, the explicit formula, what it does is, rather than writing it as, in two separate equations, like here's my first term and here's what I need to do to get the next terms, it actually takes everything and puts it in one nice formula. And what's nice about the explicit formula, like if you wanted to figure out what the 60th term was going to be, you wouldn't want to have to use the recursive formula and find a sub 2 to help you find a sub 3, to help you find a sub 4, all the way to a sub 60. If we use our explicit formula, we could just plug in a sub 60, and it'll just kind of spit out the answer for the 60th term. So the explicit formula, if we wanted, let's just make one for this example right here. We would say that a sub n is equal to, well, a sub 1 is our first term, which we already said is 5, and then plus, we want to leave this in terms of n because we want to be able to plug in different values of n here. Like if we wanted, like we said before, to find the 60th term, we would replace this with a 60. If we wanted to find the 20th term, right, we would replace our n's with 20th. So we're going to leave this in terms of n. And then D just stands for the common difference. What are we adding to get from one term to the next? So in this case, we're adding on 3. So we could put a 3 there. So this right here would be our explicit formula. Okay, a geometric sequence, on the other hand, means that you're multiplying to get from one term to the next. So let me, I'm just going to kind of make this up. So let's say we had 5, then 10, 20, 40, and so on, okay? So here, this is geometric because we're multiplying by 2 to get from one term to the next. Okay, so our first term is 5, and then 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40, and so on. So we're multiplying by 2. So geometric means you're multiplying to get from one term to the next. So let's start down here with the recursive formula again. All right, so with the recursive formula, you always want to specify, a specific term within the sequence. So I like to specify the first term. The first term is equal to 5. Now, like we said, to get from one term to the next, what we're doing is we're just taking the previous term and multiplying it by 2. So here, I'm going to write a sub n equals, well, we're taking the previous term, which I'm going to call a sub n minus 1, and we're multiplying that, so I'm just going to hit times by 2. And that's really what this says here, okay? A sub n is equal to a sub n minus 1 times r. R stands for the common ratio. That means what are we multiplying by to get from one term to the next? Now, if we wanted to make an explicit formula for this, again, it puts it all in one equation rather than two separates. So let's just follow the format of this. We would write a sub n equals a sub 1. So our first term, we know our first term, it's 5. I'm going to replace that a sub 1 with a 5. And then times r. Now, r is the common ratio. It's what you're multiplying by to get from one term to the next. So we said here we're just multiplying by 2 to get from one term to the next. So we're going to multiply that by 2. I know they put a multiplication dot here. I usually like to just put my 2 in parentheses. So I'm going to put this r in a parenthesis. I usually like to put it in a parenthesis. So I'm going to put my 2 in a parenthesis, and we're going to raise that to the n minus 1 power. So this would be my explicit formula, and this would be my recursive formula. And we're going to take a look at a bunch of examples in this packet where you have to go back and forth between the explicit formula and the recursive formula. All right, so let's turn to page 3 of our packet. So the example on the top of the page says, Jane works for a video game development company that pays her a starting salary of $100 per day. And each day she works, she earns $100 more than the day before. That's nice. Okay, letter A. If you were to graph the growth of her salary for the first 10 days she worked, what would the graph look like? All right, well, I'm just going to make a sketch of this. So we're going to have, really we just need a positive portion of the x-axis and a positive portion of the y-axis, right? Because the x-axis is going to represent days, and the y-axis is going to represent the amount of money she makes. Now, I'm going to make a small graph, so I'm not really going to fit everything on here, but let me just kind of do the best I can. So let's say we have day 1, day 2, day 3, 4, 5, 6, 7. Let me extend this a little more. 8, 9, 10. So I'm going to just put 10 there. And then if she's making $100 more per day, we would need 100, 200, 300, 400, 500, 600, 700. I'm going to have to go into the words. 800, 900, and that would be 1,000. Okay, so on day 1, she'd make $100. On day 2, she would make 200. On day 3, she'd make 300. And this would just continue on like that. Okay? So this is what it would look like for the first 10 days. And if she kept going, it would just keep going and going. So this right here, I just want to say, this is linear. Okay, it forms a line. And the reason why it's linear is because it increases by a constant amount. And I'm going to be even more specific. I'm going to say of $100 per day. Now, if something goes up by a constant amount, you're adding the same number on to the previous term. Then what we could say, actually in part B, it says what kind of sequence, arithmetic or geometric, is a sequence of Jane's earning? Well, that's going to be arithmetic. If you're adding to get from one term to the next, then that's going to tell you that we have an arithmetic sequence. So that's arithmetic. Okay, now part C says to write a recursive formula for a sequence which represents Jane's salary on day D. All right, so we know for recursive, we need an a sub 1 as well as an a sub n, right? We need kind of two separate little equations there. Actually, instead of a, we're talking about day D. So I'm going to use d sub 1 to represent day 1, and then d sub n to represent, the nth term. Okay, so on the first day, she makes $100. So day 1, she makes $100. So d sub 1 is 100. Okay, now, we know that she's making $100 more per day. So, I just wrote off to the side here, I just wrote from the previous page the formula that we use to help us with the recursive formula. So we already have d sub 1. We have our first term. Okay, they're using an a, I'm using a d. Now, in a recursive formula, a sub n is equal to the previous term plus what you're adding to it. So we could say here that d sub n is equal to the previous term, so d sub n minus 1 plus the $100 that's being added to it each day. So this right here would be my recursive formula to represent the situation. Now, in part D, they want us to write an explicit formula to represent Jane's salary on day D. All right, well, over here in this green pen, I kind of just wrote down from the previous page what the explicit formula is for an arithmetic sequence. All right, so a sub n, so I'm going to use d sub n because they're telling us here to use day d. So d sub n is equal to. Now a sub 1 would be the salary she makes on the first day. That would be her first term, so that would be $100. So we'll put 100. And then plus, now we want to leave our formula with this n minus 1 in, because you want to be able to plug in different values for n. So I'm going to leave this as n minus 1. And then we could see at the end of our formula there's a d. Now d stands for the common difference. That means what are we adding to get from one term to the next? Well, we're adding 100. So I'm going to put 100 at the end of the formula. So this right here would be the explicit formula. Okay, so let's take a look at number 5. It says, every year Michael receives a 3% raise in his annual salary. His starting salary was $40,000. Okay, so part A. Does a geometric or arithmetic sequence best model Michael's salary in year n? And explain how you know. All right, well here, this would be a geometric. And the reason it would be a geometric is because an arithmetic would go up by a constant amount. This right here is going up by a percentage, right, 3% of itself. So when something goes up by a percent like that, it would be geometric. All right, so geometric. Going to box that off as my answer, and I'm just going to say his salary, so it's a little sloppy, it's hard to write on this, increases by a percentage of itself. Okay, I'm going to put in parentheses here, not a constant. Again, if it went up by a constant, it would be arithmetic. All right, letter B says, write a recursive formula for a sequence which represents Michael's salary in year n. Okay, so off to the side here I wrote the, generic recursive formulas for a geometric sequence. So the first thing we want to do is we want to label our first term, which is going to be the salary he makes in his first year. So we could say that a sub 1 equals 40,000. Okay, now a sub n would be equal to a sub n minus 1 times r times the percent that a salary is increasing by. So let's write a sub n equals the first term, which is 40,000, right? That's our a sub 1. And we want to multiply that by the rate at which his salary is increasing. Now, keep in mind, his salary, he's receiving a 3% raise. So that means his salary is keeping its full percent plus 3% on top of that. So we're going to multiply this not by 0.03, but by 1.03. Okay, because it's, it's kind of like 1 plus the rate, right? In our exponential growth formula, you're taking 40,000, you're taking the first year's salary, and you're multiplying it by 1 plus the rate, so 1.03. So this right here would be our recursive formula. Okay, and then finally part C says write an explicit formula for a sequence which represents Michael's salary in year n. Okay, so off to the side here I just wrote the general explicit formula for a geometric series. So we could say that a sub n is equal to, well, a sub 1 we're going to replace with his first year's salary, which is 40,000. And the rate, we talked about in part B that it's going up by 1.03. We're multiplying by 1.03 to get from one year to the next. And then we want to leave our exponent as n minus 1. We want to leave it in terms of n, so we can plug in different values of n to figure out what he'll be making as the years progress. Okay, so if you turn to page 4, the next set of problems, what they do is they give you a sequence and they want you to write a recursive formula as well as an explicit formula for each of the sequences. Okay, so if we look at the first one, you first have to figure out if this is arithmetic or geometric. So you can clearly see that to get from one term to the next, we're just adding 10. So this is going to be, if you could just write this out, this would be arithmetic because we're adding 10 to get from one term to the next. Or another way of saying that, I should just write D equals 10, right? The common difference is 10. Okay, so for part A, they ask us to write the recursive formula. So I mean, down over here, I just put the general formulas for any arithmetic sequence. So the recursive is right here. Now, I usually start off writing a sub 1. I know that's at the bottom of our formula right here, but I usually put that first. So a sub 1 is our first term. And we could see that right here, our first term is 6. So let's write a sub 1 equals 6. Okay, then we want to make a rule, right? A sub n is equal to the previous term plus d. So we could say that a sub n is equal to the previous term, which we would just write as a sub n minus 1, right? One term less, and then plus d. Well, we already said that our common difference, d, is 10, so we're just going to write plus 10. So that right there would be the recursive formula. Now, the explicit formula, we're going to follow this format right here. So we could write a sub n equals, and then a sub 1, we know is 6, right? That's our first term. And then plus, and in parentheses, n minus 1, we're going to leave that in terms of n, so we could plug in different numbers for n, depending on what term we want to find. And that's going to be times d, which is 10. So this right here, it's pretty easy. You just plug in the numbers. This right here is our explicit formula. Now, what you can do with this formula if you want, like if this was, let's say, multiple choice, and they didn't have that formula there, what they could do is they could bring down the 6 plus, and if we were to distribute this 10 inside the parentheses, right, that would give us 10n minus 10. So if we wrote that as 10n minus 10, let's just combine our like terms. So we have 10n, and then if we combine our numbers, 6 minus 10 is negative 4. I'm sorry, I forgot the n. So 10n, and then minus 4. So this right here is just another way of writing this same explicit formula, right? This right here, all this is, I mean, it's just a linear equation. Like if you had y equals 10x minus 4, you could graph that. And, you know, I mean, the values that you plug into this equation will kind of spit out the values in the sequence, right? If you replace this n with a 1, 10 times 1 is 10, minus 4 is 6. So there's your first term. If we replace the n with a 2, right, a sub 2, the second term, 10 times 2 is 20, and 20 minus 4 is 16. There's our second term. And keep going, right, a sub 3, 10 times 3 is 30, minus 4 is 26. So this pattern just follows. So, I mean, you could write your explicit formula like this, or like this. Either way is fine. All right, so number 7 is, I mean, really similar to number 6. They just give you a sequence, and you have to write a recursive and explicit formula for it. So the first thing we want to do is we want to figure out, I mean, how are we getting from one term to the next? Are we adding? Are we multiplying? I mean, what's going on here? Now, if you take a look at this, I mean, to get from 2 to 2 radical 5, I mean, you could multiply 2 by radical 5, and that would give you 2 radical 5. If we multiply 2 radical 5 by radical 5, let me try it off to the side. All right, so if we take 2 radical 5 and multiply that by radical 5, well, let's see. Rad 5 times rad 5 is 5, so that's really 2 times 5, which is 10. So hey, look at that. That does bring us to our next term. If we take 10 and multiply it by radical 5, you would get 10 radical 5. If we take 10 radical 5, let's just do one more off to the side. 10 radical 5 and multiply that by radical 5, well, we'd have 10 times rad 5 is just 5. So 10 times 5 is 50, which does bring us to our next term. So it looks like what's going on here is we're just multiplying by radical 5 to get from one term to the next. So that means this must be geometric. Okay, so another way, I mean, rather than saying multiplying by radical 5, when you multiply by something, that's called your common ratio. I'm going to write R equals radical 5. Our common ratio is radical 5. All right, so since we're working with a geometric sequence, I just put the rules for the explicit formula as well as the recursive formula right down here. right, so first thing they want us to do is do, in part A, a recursive formula. So we're going to be using this. All right, so I first like to label the a sub 1. The a sub 1 is our first term, which we could see right here is 2. So we could just write a sub 1 equals 2. And then we have to say that a sub n is equal to the previous term times r. So a sub n is equal to a sub n minus 1, and then times r, times radical 5. So I guess you could just put the radical 5 in parentheses to show you're multiplying. So that right there would be our recursive formula. And, you know, so part B wants us to write an explicit formula. So, I mean, we could follow the format right off here, right? Our explicit formula, a sub n is equal to the first term times the common ratio to the n minus 1 power. So we could say that a sub n equals the first term, which is 2, times the common ratio, which is radical 5, and we would raise that to the n minus 1 power. So there we go. There's our explicit formula. Okay, so what I'd like you to do now is I'd like you to try out numbers 8 through 12 on your own. It's basically just having you write, you know, recursive formulas, explicit formulas, and, you know, feel free to look back in the packet on anything we talked about.